In this lesson, we're going to learn about the ideal gas law. So first, we're going to look back at the gas laws we've looked at. So if you recall in Boyle's law, which is a relationship between pressure and volume when the temperature and the amount of gas are held constant. So as pressure decreases, volume increases, or as volume decreases, pressure increases. So as I take my pressure and volume and multiply them together, I get the same answer. So I have an inverse relationship between pressure and volume. As one increases, the other decreases. Multiplying the two values together is going to be the same if the temperature and the amount of gas are remaining the same. So if my pressure increases, to keep it that same number, my volume would decrease. So that was our formula for Boyle's law. P1 times V1 equals P2 times V2. And then Charles and Gay-Lussac's laws, those had to do with the relationship between temperature and volume and pressure and volume. So if I keep my pressure constant, as temperature increases, the volume increases. So different pressure, but keeping it constant at this pressure, increasing my temperature, and the volume is also increasing. And then for Gay-Lussac's law, if I kept my volume constant but changed my temperature, the pressure would change. So if I were to start here and increase my temperature to there, the pressure would also increase. So here, for both of these, with temperature, pressure, and volume, both have a direct relationship, where when one increases, the other increases. We also found out here that if we were to extrapolate our data, all of them converged here at negative 273.15 degrees Celsius, which is 0 Kelvin. So here we had V1 over T1 equals V2 over T2, or P1 over T1 equals P2 over T2. So Charles' law and Gay-Lussac's law. So those are the relationships between pressure and volume, pressure and temperature, and volume and temperature. And then we looked at Avogadro's law, which was a constant temperature and pressure, and the relationship between volume and number of moles. So here we had a direct relationship again, and oops, this is supposed to be direct. So our formula here was V1 over N1 equals V2 over N2. So that now gives us relationships between multiple different variables there, and so far we have looked at the relationship in the combined gas law with pressure, volume, and temperature, and if there is a change in any of those and what happens. So here what we're going to do, now that we've looked at the relationships between volume and number of moles, volume and temperature, volume and pressure and temperature, we are going to use those to help us with the ideal gas law equation. So from Boyle's law, we have an inverse proportional relationship between volume and pressure, and we have a directly proportional relationship between volume and temperature from Charles' law, and also from Gay-Lussac's law between volume and pressure, and then from Avogadro's law, direct proportion between volume and number of moles. So what we can see with all of the ones that have volume in them, volume is directly proportional to number of moles and temperature, always in Kelvin, and inversely proportional to pressure. So what I know is that some constant times number of moles times temperature divided by pressure is equal to the volume. And that constant is R, which is the gas constant, and we can actually calculate what the gas constant happens to be. So what we can take from this relationship is we can take the P and multiply it over so that we don't have anything in the denominator, and then whatever we need to solve for, we can move things around accordingly. So the P is going to swing over, so pressure times volume is equal to nRT, so number of moles, times the gas constant times temperature measured in Kelvin. So at STP, we have 0 degrees Celsius and 1 atmosphere. And so we can solve for R, the gas constant, using that. So we know that at STP, 1 mole of an ideal gas occupies 22.414 liters of space. So that gives us our volume, our number of moles, and our pressure here is 1 atmosphere. So we have PVN, R and T is 0 degrees Celsius, although we're going to need to convert that into Kelvin because temperature always needs to be in Kelvin here. So I've got pressure, volume, number of moles, and temperature. So the only thing I'm missing is R, the gas constant. So I can actually calculate that from this. So R, to isolate that, I'm going to divide by N and T to move those over to the other side. So pressure here is 1 atmosphere, volume is 22.414 liters, so we just used 22.4 liters before, and 1 mole and 273.15 Kelvin. So one version of the gas constant is 0.082057 atmosphere liters per mole Kelvin. And so this is what you would use if you have your pressure given to you in atmospheres. So temperature, even if it's given to you in degrees Celsius, you have to convert to Kelvin. Number of moles is always measured in moles. And whatever your volume is, you are going to convert that to liters. So this is what you use if you have your pressure in atmospheres. If you have your pressure in kilopascals, so 1 atmosphere is equal to 101.3 kilopascals. And then everything else remains the same. So at STP, 0 degrees Celsius and 1 atmosphere, or 101.3 kilopascals, 1 mole of a substance takes up 22.414 liters. So we can go through that process again, this time with our pressure in kilopascals, and that just means that our answer is going to be in kilopascal liters instead of atmosphere liters per mole Kelvin. And so our gas constant when we have our pressure in kilopascals is equal to 8.314 kilopascal liters per mole Kelvin. Okay, so let's take a look at an example using that. So what is the volume in liters occupied by 49.8 grams of hydrochloric acid at STP? So we're looking for a volume. We have a mass, which we can convert to a number of moles, and STP gives us our temperature and our pressure, which can be either 1 atmospheres or 101.3 kilopascals, and then the R value we use would depend on which one of these we use. So either 0.082507, I think, and 8.314, I believe, if we're using kilopascals. So we are going to need to calculate N times R times T divided by P, but first we still need to calculate our N. Oops. I'm just going to clear that there. Okay, so our temperature converted to Kelvin, pressure is 1 atmosphere, and my number of moles is 49.8 grams divided by the molar mass of hydrochloric acid, which is 1.01 for hydrogen and 35.45 for chlorine. So that's going to give me 36, and it should be 0.46 grams per mole of hydrochloric acid, and that's equal to 1.37 moles of hydrochloric acid. So I now have my number of moles as well, and the R value that I'm going to use, because I'm using atmospheres, is 0.082, and it was 0.57, so that is rounded there to 0.0821. So here my atmospheres will cancel, moles will cancel, Kelvin will cancel, and my final answer will be in liters. So 1.37 times 0.0821 times 273.15 divided by 1. And so that is 30.6 liters of hydrochloric acid. 36 liters is the amount of space that 49.8 grams of hydrochloric acid is going to occupy at STP, so 0 degrees Celsius and 1 atmosphere.